technology, because this is on the web, so that's nice. This is an invited talk, so it's a long talk. Please,
Thank you very much for the introduction. I would like to also thank you, Alexandre, for the invitation. I'm going today to speak about warranted numerical method to classify smooth mappings from the plane to the plane. So first, I am Delanoue, and this is a joint work with Sébastien Latranche, who is also working at Angers in France. So this is the outline of the talk. First, I'm going to give you the framework, general framework, general introduction to what I mean when I speak about the classification. Second part is going to speak about the stable mappings of the plane and their singularities. I'm going to recall a term given by Whitney about normal forms. And third part is going to speak about how entire analysis can be used to compute an invariant. So with a given mapping from the plane to the plane, we are going to compute what we call the apparent contour of this map. And I'm going to finish with conjecture, prediction, and conclusion. So general framework about classification. So this is just an example. When you want to classify, you need to consider object that you want to classify. So for example, I can consider a set of square matrices of order n, denoted by n, and we also need an equivalence relation. So this is a classical one. So we can define a relation, which is denoted by this symbol, between two matrices if there exists a change of variable, that is to say an invertible matrix, such that A is equals to P times the inverse of P. And most of the time, to test the equivalence, we compute invariance. So, for example, if you have two matrices that are equivalent with this relation, the set of their eigenvalues is an invariant. Why? Because if they are equivalent, then the set of eigenvalues are the same. So, during this talk, I'm going to show you an invariant of smooth maps, and every time that you see something in red, it's an invariant. So the set of eigenvalues is not a strong enough invariant, since there exist matrices such that they're not equivalent, but they have the same set of eigenvalues. The examples can be the following. Those two matrices are not equivalent, but the 0 is the only one eigenvalue. So when you have an invariant, you would like to improve your invariant. So for example, this is a word, I don't know if it exists, but I'm going to speak about generalization. So if you take two matrices, their generalization are equal, and it's a strong invariant, a stronger invariant than the last one, because you can go back. You can go from the right to the left. So this invariant is able to test equivalence between two matrices with respect to this equivalence relation. So it was the introduction about equivalence. So with this slide, I'm going to give you an object on the first column. The second is equivalence that I'm consider, and invariance that we try to compute. So this first line is about what I've shown before. You can consider also different kind of objects, for example, real linear forms, and you can consider an equivalence, which is different than the last one. You consider that A and B are equivalent if there exist matrices U and V that are orthogonal. And of course, an invariant is given by the singular value decomposition of a matrix. So today, I'm going to speak about this last line. So the object that we are going to consider are smooth maps. And we are going to consider that two mappings, F and F prime, are equivalent if there exists differomorphic changes of variable on the source space of each map and on the target space such that f and f prime are related by this relation. So, the first part of my talk is to show you what kind of invariant can we expect to compute. So, in other words, we want to be able to have a global picture of a given map which does not depend on a choice of system of coordinate, neither on the source set nor on the targets set. Here there's a small mistake because I was thinking about application to robotics. So, in other words, the equivalence that we consider can be present like this. So we have f and f prime, two smooth maps, and we are going to say that f and f prime are equivalent if there exist diffeomorphisms. So diffeomorphisms is just smooth change of variable in the way that so g is going to be a change of variable. It must be differentiable, and the inverse map must also exist, and the inverse has to be also differentiable. So the same for the target set, such that this following diagram commutes. So it's an elegant way to present the relation between f and f prime. So here an example. So you have two maps. So the first one is 2 times x plus x, the second one x plus 1. They are in relation, they are equivalent because you can find explicit change of variable that gives you that this diagram commutes. So if I write here, we can have x, which is mapped to x plus x, sorry. Here you have x plus 2, then you obtain x plus 2 here. This map is x plus 1. So this arrow is going to be the composition of those two mappings. So it's going to be x plus 2 plus 1. So, and then you multiply by 2 to y. So you obtain 2 times x plus 3. So you obtain 2x plus 6. So the first mapping is, the first map is in relation with the second one. So now there are examples. The first one, f1 and f2 are also in relation. But here you have an example with two maps that are not in relation. First one is this one, and the second one is something like x plus 1, something like this. And I'm going to show you why they are not in relation, because we are going to compute an invariant for this one, compute an invariant for this one, and invariants are different, so we can conclude that they are not in relation. They are not equivalent. So why? Let me show you with this picture. So imagine that you have a map in the one-dimensional case from R to R. Here you can see the source set and the target set. If you make a change of variable on the x set, you're going to just map different point to different position, and the same for the y set. And what's going to happen is that your map is going to be changed a bit, but what's going to happen? Singularities of f, the number of x, such that the derivative of f is equals to 0 is going to be the same. So it is not possible to avoid singularities of the map f. So that's why those two maps are not in relation. They are not equivalent. So first, maybe an easy proposition, but I think it's important. So imagine that you have two maps, f and f prime, that are in relation, and here you can see that the image of x1 is y1 and so on. Then the preimage of y1 is homeomorphic to the preimage of y2 by f prime. This is just given by the change of variable g. So the preimage are homeomorphic. Homeomorphic means that they can be mapped to each other through a continuous function map. So this is the first proposition. The second one is about singularity. So if you take two maps F and F prime that are equivalent, the rank of the Jacobian matrix of F at x1 is going to be the same as the rank of the Jacobian matrix of F prime at x2. The proof is really easy. All you have to do is to apply the chain rule. So you apply chain rule to F. As you know that F is equals to H times F prime, not times, H composed with F prime and composed with J. The chain rule gives you this, and as you suppose that two maps G and H are diffeomorphic, you know that this matrix is invertible, so of course the rank is not going to be changed. So this can be seen as an invariant also. More seriously, we are going to consider the set of subset of the source space such that this matrix, the Jacobian matrix of F, is singular. And what is very important to me is that to see that if F and F prime are equivalent, then the topology of the critical points are the same. That is to say that those two sets, SF and SF prime, are homomorphic. So this you can say this way: the topology of the critical point sets is an invariant. So let's see this with examples. So here you have two maps, F and F prime. So in both cases, the set of singular points is just a point. This point in this case, this point, but they are not in relation. This comes from singularity theory. Imagine that you make a change of variable with x or with y. The minimum is going to be a minimum, or it can be a maximum. Because if you map y to minus y, you're going to flip all the map. But in this case, there is no minimum, so of course they are not equivalent. So it can be explained with singularity theory and more generally with Morse theorem. So let's see, in my point of view, a more difficult example. So here we have two maps, 4 critical points, same for the second one, 4 critical points. Here you can see in red the global minimum and the global maximum. As you can see, the global minimum and the global maximum are between a local maximum and a local minimum. So if you make a change of variable in x or in y, what's going to happen? The global extremum is going to be inside of an interval defined by a local minimum or global maximum. But in this case, this is not the same thing, because the global maximum and the global minimum are not inside local extremum. So that's why those two maps are not equivalent. So we're not going just only to consider just the set of singularity, but also how they are connected, how these different singularity are connected. So what can we do in the one-dimensional case? We can first compute with interval analysis, for example, 2 points. This is a place where the derivative of f is equal to 0. Then we have to also just create two another symbol, B1 and B2, to remember. Then you also compute the pre-image, the counter image of B1 and B2, to remember how they are connected, all those singularities. And we are going to create a graph from graph theory, connecting all elements A and connecting all elements B according to the topology of the source set and target set. And then we're going to store that A0 is mapped to B0, A1 to B1, and so on. And also A3 is mapped to B1. And at the end, you just have a graph and a relation between two graphs that is going to store all the information that you need to test the equivalence between two maps in the one-dimensional case. So to consider, for example, in the two-dimensional case, I need a generalization of a graph from graph theory, and this is classical. This is what we call a simplicial complex. Here, definition of a simplicial complex. So this is given by a set of what we can say nodes like graph theory. This is just symbol. And a simplicial complex is a subset of the polar sets satisfying this property. And this property means, okay, I'm going to show you with an example. This K is a simplicial complex. So this is just a list of symbols. Here you can see this is its nodes, here its edges, and here, okay, if you just forgot about this line, you can say, okay, this is just a graph. And we need more. So we're going to, maybe we could have triangle and tetrahedron to extend a graph theory from graph theory. So what this relation means, it just means that if you have a triangle, the boundary of the triangle must be inside the simplicial complex that you consider. So for example, also if you have this edge, A0, A2, it means that you also have A2 and A0 inside your simplicial complex. So now I'm going to give you maps between simplicial complexes. So given two complexes, K and L, a simplicial map, this is just a map defined between nodes, such that we need this property. Each time that you have a simplex, it can be a line, it can be a triangle, the image of each element must be an element, must be a simplex inside your second simplicial complex. This is what we want. So an example here. So K, it's just a simplex created with just a complex, sorry, with three line segments. The second one has two line segments, and I'm going to map those four elements to elements of L, and this is a simplicial map. So you can imagine this as the line red is mapped like a fold inside the same place where the green one is mapped. So here an example which is not a simplicial map. Why? Because I consider the same complexes as before, but I have decided to map A3 to B0. So this line segment does not belong to L, so this is not a simplicial map. So this is a kind of generalization of map between a graph. You just want that when you have a map between nodes, and if these nodes are connected by an edge, then the image of the node is also connected at the end. This is what we do. Okay, so we can also speak about a simplicial map in higher dimension. So here this simplicial complex is defined by a triangle. This one is just one triangle, and the simplicial map here, this is a map that is going to fold the first simplicial complex along the black axis. So, to be able to compare a simplicial map with a smooth map, it is difficult, so I'm going to relax the first relation I've considered. Here's the same as before, except that the change of variables are not smooth, but just continuous. So this is what we said that when f and f prime are topologically conjugate. So of course, if two smooth maps are equivalent, then they are topologically conjugate also. And this is the definition that we propose. We would like to be able, and I was thinking that I should be able to compute this, but you will see that I was not able for a moment. So I would like to compute what I've called the portrait of a map. So given a smooth map, a simplicial map is a portrait if they are topologically conjugate. So here is a bit strange because we compare a smooth map with just something which is combinatorial, and of course we have to do a kind of realization of this combinatorial map to be able to speak about, but this is classical in algebraic topology. So, for example, the simplicial map given here is a portrait of this smooth map. You can make a change of variable between this that is going to be mapped on the x-axis, and this one is going to be mapped on the y-axis such that a diagram commutes. So here you have a smooth map, and this is what I want to compute, a simplicial map such that this simplicial map is a portrait of this smooth map. So there exists an horrible theorem. This theorem is variable. It tells you that each time that you have a closed subset of Rn, there exists a smooth map, a smooth function, such that this relation is true. So the thing is that we are not going to consider all cases. We are just going to consider a subset of a smooth map. We are going to consider smooth maps that are stable. So it's a big theory coming from singularity theory developed by René Thom and John Matter. A smooth map is said to be stable if there exists a neighborhood such that for each function inside this neighborhood, the two maps are equivalent. So first example, x squared is a stable map, but this one is not. Why? Because if you think about this map, parameterized by epsilon, if you take epsilon equals to 0, you obtain x up to 3. And of course, each time that that epsilon is non-zero, this is the map that you're going to have something like this. So of course, this one is not equivalent. This one. So this is x squared. This is x minus x. Epsilon. So they are not equivalent, except the case where epsilon is equals to 0. So this is not a stable map. And during all the presentation, I'm just going to consider stable maps. So now I'm going to focus on two-dimensional case. Because in the two-dimensional case, we have beautiful theorems that have been proven by Whitney and generalized by René Thom. So if you have two-dimensional manifolds, if you consider a map F which is generic, you can say each time that you see generic in my slides, it's the same as stable. So in the two-dimensional case, this is equivalent. The set of critical points is a regular curve. And if you take a point on this singular curve, just one of those two cases can happen. So let me show you a geometric representation. So what can happen? Here you have in red the singular curve. It's always a curve. This is the source set. This is the target set. So in this case, the tangent space to the curve is not the same as the kernel, and the kernel of the Jacobian gives you the direction in which the fold occurs. So here you can see it's a fold point. So this is just you have this is the source set, and this is the target set, and here you can see a fold curve. And this is just like this. So this can happen generically. This is stable. And the second property that can happen, so imagine you have something which is a fold here. You can also a second fold, so you can have two curves of fold, and they can vanish at one point, and this point is going to be called a cusp point. This is also something which is stable. This is generic. This has been proven by Whitney. And Whitney have also given two normal forms. So the first case gives you, okay, it's just you have your map, and it's just a fold. And the second case, you can find a change of variable such that your map is equivalent locally, this is important, locally, to this map. So this is the smallest expression that has been found. So maybe I can put it in red. You can see fold point and cusp point is written in red. So this is invariant. So this is the thing that is going to be true if you change if you apply a change of variable. So Whitney has proven this, but this is just local property. And I want to be able to compute global property, global invariant. So let me define what we call the apparent contour of a given map. So this is, okay, we're going to consider, this is a bit technical, but we're going to consider that our source set is a simply connected compact subset of R2. It's just a ball, you can imagine that this is a ball. And with a smooth boundary, this one. And the apparent contour of F is given by, this is the image of the singular set, in this picture, union the boundary. So the apparent contour, this is this. Not the set, but just the lines. So this is what I want to compute because it's an invariant. So what I'm going to compute? I'm going to try to find A going to be a cusp, B also a cusp. Here you can see a line of fold points. So it's going to do like this. And here also a line of fold points. So this area is going to be mapped to this one. Can you understand this picture? This part is going to be folded like this. So that's why you think this part is full. And also, this part is going to be mapped up, and this one is going to be mapped to this one. So this can happen generically. If you take a function, for almost function, this can happen. So what I'm going to compute also, to have a global property, here I'm going to compute those 2 points, C1 and C2, because they are mapped to the same point, the same for D, and E1 and E2, this is 2 boundary points that are mapped to the same E. And also F and G, 2 points here. So this is what I want to compute. I want to compute this. This is an invariant, and this is important because I can test equality or non-equality between 2 maps, just computing this. So we had to generalize the Whitney theorem to take into account global property. So global properties of generic map are the following. This is just in the 2-dimensional case. Okay? So the first point is this is just the Whitney theorem. It tells you that the set of singular points is a regular curve, and moreover, elements of S are 4 points or cusp, and the set of cusp is a 0-dimensional manifold. So second property, which is our contribution, 3 singular points do not have the same image. This is not stable to have 3 singular points that are going to be mapped to the same one. Moreover, 2 singular points, so here, maybe 2 different singular points. So this part is going to be mapped to this one, maybe. It's a fold. This is a fold also. And those 2 points, maybe this one and this one, are going to be mapped to the same. And at this point, they have normal crossing. So we have the same property for the boundary. Three different boundary points do not have the same image. Two boundary points having the same image cross normally also. And we can have also a theorem with a mixture with the boundary and the singularity points. So, okay. And also the boundary with the singular. Yeah, this point must be considered also. So, this is all the cases that we are going to be able to handle to create an algorithm able to compute the apparent contour of a given map. So let's focus first on the first thing. This is what we call a cusp. So a cusp is a kind of horrible point in the sense that this is a singular point, but if you consider the map restricted only to this singular curve, there is also a new cusp, a new singular point, a new singularity. It's a kind of singularity of singularity. So we have proposed to write this in this way. And if you consider this map, this is just a map that computes the derivative of the Jacobian of f at p times a vector. This vector Cp is defined by this expression. And the first important property is the following. If Cp is equals to 0, then P is a cusp. And it's also true in the opposite direction. And this one, this Cp is invertible. It's also important because we are going to use interval Newton method to compute the 0 of C. And each time that you have a 0 of C, you know that you have a cusp point. So, geometrically, what does it mean? The vector field is defined on this. The vector field C is a vector field that, if you solve the ordinary differential equation defined by this vector field, you obtain a parametrization of the fold curve. And here you can see the red line. The red line is the kernel of the Jacobian, and if this is equal to 0, it means that the vector field, vector at P, is in the kernel. That's all. Okay, so again, this is where we use interval analysis. Interval Newton method is a very good, efficient algorithm to enclose rigorously 0 of a given map, and this is the map that we are going to consider to find cusp point. Also, we are going to consider two different folds. So what we do have to find? We have to find 2 points that are singular, but different. So that's why I have to remove this diagonal, such that they have the same image. But I have also, I need also to find just one couple, not pairs, just couple. If I find x1, x2, it's the same as finding x2, x1. So that's why I question by this equivalence relation. So, okay, let's speak about the quotient relation that we consider is. We are going to have an interval-based method with a special bisection scheme. Let me express. So this is not easy to draw because we are in the 4-dimensional case. So we have the source space also. And each time that we create a subdivision of this set, we are just only to consider, for example, this blue set is the same as this one according to the last relation. That's why I'm not going to consider every set which is under diagonal. Okay, this is the bisection scheme. And also what is really important, the previous slide, you can also create equations. So what does it mean that x is inside the singularity curve? This is just the determinant of the Jacobians, which is equals to 0 for the first point, for the second point also. And you also need that each component is mapped to the same. One for x1 and x2. And here it's incredible that you have 4 equations and 4 known. So again, we can use entire Newton methods to find such a point with this scheme. So there exists a problem. The problem is on the diagonal. So we have proven diagonal. So the first case, let's finish, and entire Newton method gives us the solution. But the second case, it's more difficult because we want to prove that our map, restricted to its singular locus, is injective. So we want to prove that we are in the first case, but not in this case. We want to prove that there is no self-intersection. It's a bit difficult, but we have this technical term that proves us that this does not happen, and our dissection scheme divide the set until this property is satisfied. Okay. This is technical. I'm not going to speak about this. This one is horrible, but I want to be complete, so that's why. So the last proposition is not satisfiable if you have a cusp. So we had to propose a horrible theorem with third derivations on the difference. So for the boundary we have the same approach. So for the boundary, the boundary is defined by an equation. So we have an equation for the first point, an equation for the second point. We also need those 2 points as mapped to do the same. So so we have the same approach and it works. So okay. So this is what we compute. We divide the source set until we know the topology of the singularity set. We also have proven blue points that are points that are very special in the sense that it can be a cusp, these 2 points. It can be also a point that have the same image as the boundary point, and so on. And at the end, this is the output of our algorithm. I know this is horrible, but this is the output that we compute. We just create a graph. So this is the incidence matrix of the graph. Here, how can I see it? For example, E6, this column, is connected 2 points, and I'm going to store this information, is connected F and G. And for example, E9 is connected A and C1. A and C1. So this is the output of our algorithm. But this is the topology of the singular set, and this is not an invariant. What is an invariant? This is the image of this singular set. So it's very easy to go from this matrix to this one. Just forget, each time that you have C1 and C2, you are going to just add those 2 lines, and it creates an incidence matrix, which is a graph which is homeomorphic to the apparent contour of F. So, okay, this is technical. Our conjecture is the following. From this graph and the way it is invaded in R2, it is possible to compute a portrait of F. So this is a combinatorial object which saves all information of a given smooth map. So this is the approach. So if you want references about this talk, you can find our last article, which is going to be published next month, with all technical things. And more generally, if you want to know more about the stable mappings and their singularities, there is a beautiful book by Bobolowski and edited by Springer. So, I think I have a short time to speak about application. Yes? So, application, what can be used for? imagine that you have a robot, and your robot, you have this an effector, and of course you can write an equation for the on the effector depending on the element that you can control. This is the configuration space. So this map is a way to understand the robot. But the robotician can consider different coordinates in the configuration set or different coordinates for the working space. So our approach is to be able to compute intrinsic properties of a robot in the way that we compute intrinsic properties of the map. So let me show you how can it help for motion planning. Motion planning is the following thing. Most of the time, you want that your robot follow a path for the end effector. So you just have this kind of path, defined by gamma, data, sorry, and you have your map, and what you want to find is a path in the source, the configuration set, such that this path is mapped through F to delta, and if you take into account singularities of your map F, you can understand that for this special path in the working space, there exists two solutions to this problem. Why? Because this trajectory is going to touch a singularity of the robot. So there exists two different ways to follow this trajectory in the working space. You can see two solutions to this problem. So we have now a PhD student working on this. His name is Romain Benoit, and he has also proposed a paper to this robot. This is an horrible robot not so horrible, but it is horrible for us because equations are more difficult to handle, but it works also with this kind of robot, a three-dimensional robot, three-dimensional configuration space and three-dimensional working space. This has been extended to the three-dimensional case. So in conclusion, I would like to say that my source code of this program is available on my webpage. This has been implemented. You can download it and compute it and with your example. And I would like to thank you for your attention and thank you again, Alessandro, for the invitation. So if you have any question, I'm here. This one?
So you say that you have two solutions.
Yes.
But the two of them will find the singularities, no?
Yes. It's going to be touched maybe here.
Okay.
The singularity for this robot is just the alpha axis.
Okay.
In this case, where the robot is in this case, you can choose like this or like this.
Okay.
That's why.
So you have no way to avoid the singularity.
No, it's not possible. You have to take into account singularities to have a good understanding of your robot. To understand the behavior of the robot, you have to know where are the singularities. This is my point of view.
And so did you study this map from alpha?
Yes, we did it.
So we didn't see the...
Yeah, I can show you if you want. You want?
Yes, if it's not...
So this is not easy to understand, but this is a kind of graph. We have a map from R2 to R2, so it's the graph is in a four-dimensional space. So what we can draw is the following. Just imagine that this point is mapped to this one. So what is this map, it's a kind of fold along this axis. And the fold is mapped to this one. So sometimes there is two solutions. For example, the pre-image of this point is composed by 2 points, but this one has only one pre-image.
Okay, so the trajectory, if you can also draw the trajectory of the
Yes,
reference
it
map.
touches the boundary. So
And the initial point,
it's going to be somewhere here, maybe. So it's going to be like this. You touch and come back. So as soon as you touch the singularity line, you can choose.
but you have to show also that you cannot avoid the.
Yes, you cannot go outside of the.
No, your path, there is no possibility to have a path from your initial point to your final.
Yeah, it can happen also, but
Because you are out in the blue one. And
yeah. Well, I was somewhere here.
Okay, then you have to go. Okay.
Another question?
Yes, that's it.
So, if I understand well, this is of course just from the application. So on the left is the joint space.
Yes.
And the right is the
Working space.
Working space. But somewhere you choose the path in the joint space that will go through the singularity.
Yeah, I did not choose it. I think that the problem for the robotician, he has a path inside the working space, and he wants to find a
Okay.
path in the
So it's the path that it has been chosen in the
configuration space.
configuration space that will go through the singularity.
Yes, that's
Okay.
it.
So another question is that do you think you can use your methods to compute the working space, the boundary of the working
Yes, we
space
could.
for a robot, and also generalize to the aspects of a robot?
Yes, so Romain Benoit, who is working with us, his supervisor is also Philippe Vanger, who is a robotician.
So that answers the question. I also was wondering whether you could extend to redundant robots because you have you don't have any redundancy, any kinematic redundancy because you have three. If I understand well, you have 3 degrees of freedom altogether.
Yes. So this is going to be generalized by Romain. He's also working on this the things.
But then the singular space would be.
It can be a curve, it can be a
Okay.
surface. So he has to be on top of this.
Another question? Maybe on the theoretical part, when you were talking about apparent contour or portrait of F with C1 and C2, I don't.
This one?
Maybe I lost something, but why do you merge C1 and C2?
Because they are mapped to the same point. So
How do you know this?
I know this because when I compute blue points, I know that this is a cusp. I also know that this one is going to be mapped to this one also, so that they are connected through F because they have the same image. I know this. That's why I have named this one C1 and this one C2, because I know that they are mapped to the same through F.
And then what was the meaning of the incidence matrix?
The meaning of the incidence matrix is how these points are connected.
Oh, okay.
So for example, E10 means that the A is connected to